Okay, so this is the second lesson in chapter 7, limiting reagents. So, or reactants. Reagent is a fancy way of saying reactant. Okay, so this is a really practical calculation because usually if you have more than one reactant in a reaction, which is the most common, then one of the reactants has to be used up first. It's very rare that you're going to have exactly the same amount of both reactants. So again, we're always going to consider and compare moles. So we don't measure moles, like we don't have a scale to measure moles like we do grams in a lab, right? So most people have a volume if they're using a solution, or a gram amount if they're using a solid. And then what they'll do is they'll have another reactant that is obviously way more than they need. So we have one reactant that is completely consumed in a reaction, which is the limiting reagent. It limits how much reaction can occur. And then there is the excess reagent. So you may not have even noticed this really, but some of the questions will even say that, will have said that already. Hydrogen, 10 grams of hydrogen reacts with excess oxygen, even in questions where you were just asked to calculate moles, even before we maybe did stoichiometry. So what that is doing is just saying it doesn't matter how much oxygen there is, because we know there's way more than we need. So it is not going to limit how much reaction can occur. So it's going to be, the limiting reagent is going to be completely consumed. And once it's used up, the reaction is going to stop. So that's a part of the other word about, or part of the other meaning behind limiting. So once the reaction stops, it limits how much product can also be produced. So that's important. So today we're going to look at calculating or figuring out which reactant, if there is 2 reactants or 3, which reactant is going to be used up first. There can only be one limiting reagent, thus limiting how much products can be produced. So then on Thursday, the lesson will be percent yield. So how efficient, we can use that as a measure of how efficient the reaction is. How much did we get compared to how much we should have gotten? Okay, so the other reactant or reactants that are completely, if you want to add that there, that are not completely used up. So you can have more than one excess reactant. Okay, so if you are given 2 or 3 reactant masses, you must decide which one is the limiting reagent first. Now, normally the question will say blah, blah, blah reaction, and then part A will say find the limiting reagent, and then part B would say calculate how much product is produced. Part C would say calculate how much of the other reactant is still left over. So usually, like it says here, you have to figure out what the limiting reagent is first, and that's what you'll be asked to do first as well. So we're going to use mole ratios, which is stoich, of course, to determine the limiting reagent. Oh, it says stoich right there. And if we are going to be doing stoich, then you need to have a balanced chemical equation. Okay, so this question, or these 2 questions, it's missing an arrow, sorry about that. The first 2 examples we're going to do are going to look at a limiting reagent if you already have moles. Okay, so again, we're never going to compare grams, only moles. So here you have, and we kind of actually already talked about this a little bit about stoich ratios and what the mole amounts actually mean. So here in our reaction, we have silver nitrate, 1 mole of silver nitrate. So add in those ones if it's not super obvious to you. 1 mole of silver nitrate for every 1 mole of sodium chloride reacts. So then that means that, I'm just going to rewrite that. And then it's saying, okay, but in our lab, we have 2 moles of silver nitrate and 2 moles of sodium chloride. So they have equal mole amounts, equal coefficients, then they're going to be used up equally. So if you had, let's say you had 1,000,000 moles of silver nitrate, you would need 1,000,000 moles of sodium chloride in order for the reaction to occur. So when you have this kind of situation, it's simple. The mole ratio is simple. And then, there's certainly math you can do to make sure you have the same mole amounts. Normally, one of them will still be in excess. For example, sodium chloride table salt is really common. So you'll have the limiting reagent would be something like silver nitrate because it is rare and more expensive. But here, equal mole amounts, equal coefficients mean they are used up equally. So therefore, either of them is the limiting reagent. So I'm going to use the short form LR. Okay? Well, wouldn't it be nice if it was always this easy, right? Okay, so let's look at another simple example. 2 hydrogens and 2 oxygens make two hydrogens and 1 oxygen. So again, write that one in if you want, to make 2 waters. So now we have 2 moles of hydrogen and 2 moles of oxygen reacting. But here's a problem because now the coefficients are not the same. So that means that you can't compare these directly. We have to do a little bit more math, or we have to look at the ratio. So one of the things we can do to kind of streamline the stoichiometry process is consider what the coefficient is without actually having to write the whole ratio out. So if we wrote this ratio out and you were going to compare them, then essentially in the end, what you would be doing, one of the things you would be doing is dividing by the coefficient. So basically bringing it all down to a coefficient of 1. So then this number here that we're going to get, so now this turns into a 1 and this turns into a 2. This is not the mole amount. It is not the coefficient straight up. We've sort of manipulated it. So we're going to call that the limiting reagent ratio. Okay, so that is the mole divided by the coefficient. And then using the limiting reagent ratio allows us to compare, allows for comparison when the coefficients aren't the same. Okay, so back here, we could have done it, right? We could have divided by the coefficient of 1, and we would have gotten the same answer still. So when you have the same coefficients and same mole amounts, then that is very, very straightforward. But here we don't. So now once you look at the limiting reagent ratio, now you can say, oh, well, they aren't equal because every reaction requires double the amount of hydrogen to occur. So that means it's going to be used up faster. So then now when you look at the limiting reagent ratio, then hydrogen gas is the limiting reagent. So there are plenty of ways to think about this. Like I said, you can think of it like that there is twice the amount of hydrogen that's required for every cycle of the reaction, so it's going to be used up faster. You can just look at how if you divide by the coefficient, then you're bringing it down to being able to compare when the coefficients aren't equal, like you're kind of getting rid of the coefficient or trying to cancel it out. But then the important part is when you have a lower limiting reagent ratio, that is going to be the substance that is the limiting reagent. So when you have a lower amount, then that is indicative of, oh, if you don't have as much, then it's going to be used up first. Okay. Not super straightforward. Okay. So, but once you do a few of these, it'll make a lot of sense. Okay. So now we have a real reaction. Hydrogen sulfide and sodium hydroxide is going to make sodium sulfide and water. If you react 3.2 grams of hydrogen sulfide and 4.55 grams of sodium hydroxide, how much Na2S will be produced, how much water will be produced, how much excess reagent will be left unreacted. And actually even, like I said, I would even make this more, I would make this even more emphatic. I would write determine the limiting reagent. And then I would call this B, C, D. So similar to the one strike example we did, we're going to do a lot of work for part A, and then part B and C will be a little bit more straightforward, and then part D is a little bit tricky as well. Okay? All right, so let's do, what do we always do with grams first? Well, we're always going to change grams into moles. Okay, so I'm going to set up the table very similar to what we have done in the past. We have mass, molar mass, and moles. I've already got the molar masses in there. We are eventually going to find water as well, but for now, like I said, B and C are pretty straightforward. It's the excess and the first part that takes a little bit of work. Okay, so we're going to do moles. Again, it's mass over molar mass, so this line divided by this line. So 3.2 divided by 34 is 0.0941. 4.55 divided by 40 is 0.11375. Okay. So now we need to decide which of these mole amounts we are going to use, because the question asks us for sodium sulfide. So in order to calculate the sodium sulfide, we need a mole amount. How are we going to get a mole amount? We're going to use stoic eventually, but we want to use, right, to convert one mole amount into another. But this time, this question is a little bit different because now we have two. We have H2S and we have NaOH. So which one do we use? Well, we're going to use the limiting reagent. So again, the limiting reagent is the one that has the lower amount. So it's used up first. But if they don't have the same coefficient, you can't just do the two steps we've done so far and that's it, okay? So we need to take into account what's its coefficient. So if you want, you can write down the coefficient to draw your attention to it, and then the limiting reagent ratio, you just divide by the coefficient. I realize that you might say, oh, well, obviously 0.0941 divided by 1 is 0.0941, which is fine. I'm showing all of my work here, okay? So then we get 0.569. So this limiting reagent ratio is different because the coefficients are different. So every time a reaction occurs, you need twice the amount of sodium hydroxide. So just looking at the mole amount doesn't give us a complete clue or a complete idea about what's happening in the reaction. So every time a reaction occurs, if you get rid of the coefficients, you need 0.0 you have 0.0941 of hydrogen sulfide, but only 0.0569. So the lower amount is going to be used up first. So sometimes students, you can write a sentence. Sometimes students will do something like this to show me that it's the limiting reagent. You can write a sentence. Okay, it's really up to you. Okay, so now that we have the limiting reagent, why is that so important? Okay, so the limiting reagent runs out first. So once it's gone, that means the reaction stops. So once the reaction stops, can any more of the other reactant react? No. If the reaction is stopped, can any more of the product be produced? No. So then the moles, the mole line, the N line of the limiting reagent can be used to determine how much product is produced. Please remember this LRR, we wrote a little thing up here, allows for comparison when coefficients aren't equal. That's it, okay? It is only used for comparison purposes. We are going to use, as always, the mole amount in the stoichiometric ratio. That's what's the most important, okay? So now we are finding Na2S. So I'm gonna write it down even here one more time. Okay, so whenever we are similar to the last section, whenever we're comparing one amount to another, we're going to always use moles, and we're always going to use the stoichiometric ratio. And then, so over here, we kind of drew the arrow for stoic like we did in the other one. So this is going to come from the limiting reagent. So if you want to make sure those connect there. Okay. All right, so we are looking for A or B, depends how you look at it. We're looking for Na2S, so similar to what we did before. How many moles of Na2S? Its coefficient is 1. We have 0.11375. That is from the mole line. Okay. So again, cross multiply or decide however you like to solve this ratio. Okay. It does ask for grams, I believe, in the question. Oh, well, it doesn't really, but if we change it back to grams. When we do percent yield, it will, so might as well practice that. I believe in the chart, we also already wrote its molar mass here. And I'm running out of room, sorry. Don't tell Mr. Todd I wrote 2 equal signs on a line. Okay, 4.44 grams of Na2S. Okay, so then how much water will be produced? We are still using moles of the limiting reagent. So this question would actually be worth probably like 2, like not very much, because we don't have to go through all those steps again. We can jump right into the ratio because we already know which one is the limiting reagent. So we're still using the 11375. Now they have the same coefficient, so they've got the same mole amount. And again, we'll change her back into grams. Okay, so not so bad. Okay, but now when we get to the excess, there is a little bit more work we need to do. Okay, so how much excess will be left unreacted? So this all I've done here is, because it was a long time ago, I have included the end line from your table. So if you don't want to write this out, you don't have to, because you guys can look at your note, okay? So we calculated what the limiting reagent was, the 11375 moles of sodium hydroxide. So what we're going to do is we're going to pretend like we don't have this H2S for a second. We're going to pretend like if we were just given the sodium hydroxide, let's calculate how many moles of hydrogen sulfide have to react first. And what a shocker, we're still going to use because once the limiting reagent is gone, the reaction stops. Once the reaction stopped, no more of the other reactant can react. So it limits not only how much product can be produced, but it also limits how much of the other reactant can react. Okay? So then its coefficient was 1. So all of our stoichiometric ratios had on the right-hand side, like the value we know, I guess, or the given value was the limiting reagent. It's so important. It limits how much reaction can occur all across the board. Okay, so this is weird, right? So now it's like, but Ms. Todd, we have 0.0941. Even though I crossed it out here, it's still there. Well, this amount here, this is how much is used, right? Once the reaction stops, then there should be some H2S left over. So check your answer. Is 0.0941 larger than 0.0569? Yes, it is, which makes sense. It's excess, which means leftover. Okay, so, and how do you figure out how much is left over? If you have a pizza with 10 slices and 8 people eat one slice, how much is left over? You would subtract. So that's all we're going to do. We are going to subtract. So we're going to find what's left over. So the moles of unreacted H2S is going to be how many moles we started with minus the number of moles we reacted. So this is the started with here. And when you add and subtract, they have to have the same unit, right? So make sure you're not subtracting the grams by accident. Not that you would ever compare grams anyways, but just in case. Okay, and then if you have to change it into mass, usually I'll try to be really emphatic, like how many grams instead of just amount. Your textbook uses amount to usually mean moles. They don't usually say amount in moles. They would say just amount for whatever reason. There is a variety of ways to do this. You can convert, like you have this amount in grams. You could have converted this into grams and then this amount here into grams and then subtracted. It doesn't matter. But once you subtract, you have to have the same unit. And when you do stoichiometry, you can only compare moles. Okay. So we started with 3.2 grams. So once we subtracted, we were left with 1.26 grams left over, which makes sense. That is less than 3.2. Okay, so there are on D2L, there's a few textbook questions listed. There aren't a ton. Obviously, these problems are a lot of work, but it's just one of those like procedural things, like just do the steps. And again, it is sort of the same steps we've been doing for a while. Change mass into moles, and then a little bit of difference in what we do with that and how we compare. Okay, thank you.